All right, today is a big day. Today we are going to start learning about what to do when we can't just use geometry to get areas. So, as a review, the integral from A to B means find the area between the curve and the x-axis from A to B. Sometimes we can calculate these areas using geometry formulas. That's pretty much all we've been doing for a while. But the big idea of today is, what do we do when we can't get exact areas using geometry formulas? Well, if we can't get exact areas using geometry formulas, then what we're going to do is estimate areas using specific geometric shapes. So we have 4 ways of estimating areas. And we used the activity today to help you visualize this a little bit. But here's what it is formally, like if we were to give it a definition and explain how to do the problems. So we have something called Elrom, which is the left rectangular approximation method. Sometimes this is called a left Riemann sum. And the reason it's called a left Riemann sum is because a guy whose last name was Riemann invented it. So here's what this says. If we can't get this exact area, because this is not a perfect rectangle, it's not a perfect triangle, it's not a perfect semicircle, then what we do is we divide this up into sections. We choose the left side of each section and we make rectangles. So the first section goes from 0 to 1. The left side of that would be at 0. So I would make this the height of that rectangle. Then the next section goes from 1 to 2. So I would make the left side the height of the rectangle. And the last section goes from 2 to 3, so I would make the left side the height of the rectangle. Now, a second way to do this is a right rectangular approximation method. Or sometimes this is called a right Riemann sum. And again, we're going to divide up our graph into sections called subintervals. But instead of choosing the left side of each section to make the height, we're going to choose the right side. So from 0 to 1, the right side would be at 1. So my rectangle would be this height. Then from 1 to 2, my rectangle would be this height. And then from 2 to 3, my rectangle would be this height. So my rectangles this time would look like this. Now you'll notice that these rectangles were what are called an underestimate. They're all a little bit too small to get the exact area. We have these missing chunks of area that we're not accounting for. These rectangles were all a little bit too big. So we've got these extra chunks of rectangles that we didn't need to get the area underneath the graph. So sometimes instead we use what's called a midpoint rectangular approximation method. Or sometimes we call this a midpoint Riemann sum. And instead of choosing the left endpoint or the right endpoint to make our rectangles, we divide our graph up into sections. We find the middle of each section and we use that y value to make the endpoint. So this is the middle x, and we use that middle x's y value to make our height. So our height would look like this, and then our height would look like this, and then our height would look like this for each of our rectangles. Now this is going to be the better of the 3 rectangular approximation methods, because each of these rectangles is a little bit too big and also a little bit too small. So you can see we have little pieces that we didn't account for, but we added in some pieces that were extra, so it ends up kind of balancing out. You end up with a better approximation when you use this method. But the best approximation method that we're going to learn is what's called the trapezoidal approximation method, where and sometimes this is called a trapezoidal Riemann sum. Where basically we divide up our graph into sections, and instead of making rectangles, we use the beginning and the end of each section, and we make trapezoids. Like that. Now, one thing that is a little bit tricky about this is that normally when we see trapezoids, like in geometry and stuff, trapezoids always have parallel lines at the top and the bottom. So when we find their areas, we usually call this the height, base 1 and base 2. But all of our trapezoids in these problems are going to be switched around. And they're going to look like this, where this is going to be the height, this is going to be base 1, and this is going to be base 2, because all of our parallel lines are vertical this time. So it is something important to watch out for when you're using trapezoids and you need to get their areas, that you recognize that the height is actually sideways this time, or what we call the height is actually sideways. All right, so let's look at some examples. When we use LRAM, RRAM, MRAM, or trapezoidal approximation methods, we do not get the exact answer. And that's really important to recognize. We are estimating. These are not nice geometric shapes. So we cannot get nice exact answers. Instead, we're using an estimate using geometry. The size of your subinterval matters. This is also a second really important key information. The subinterval is how wide you make your shapes. If you have smaller subintervals, you have a better approximation to the actual area. We saw this in our examples that we tried today in class. When we only had 3 rectangles, we had a lot of extra stuff hanging over. This wasn't a very good estimate. But when we made the rectangles narrower and we made more of them, we had less extra stuff hanging over. Our estimate got bigger. So let's take a look at this graph. I've already given you the graph of x squared plus 3. We want to estimate the integral from 0 to 4 using the specified type of approximation and the number of subintervals. So for number 1, we want to estimate it using RRAM, or the right rectangular approximation method, with 4 subintervals between 0 and 4. It's going to be very important that you are able to visualize and draw these pictures. So because we want to integrate from 0 to 4, I'm going to draw a line at 0 and a line at 4 as the beginning and the end of the area that I'm trying to estimate. Now it says to use 4 subintervals. So between 0 and 4, if we make 4 subintervals, the graph divides up nicely at the integer x values. So by drawing in these lines at 1, 2, and 3, I make 4 subintervals. Now our RAM says choose the right side. So between the 0 and the 1, the right side is the 1. So this would be my first rectangle. Between the 1 and the 2, the right side would be the 2. So this would be my next rectangle. Between the 2 and the 3, the right side would be the 3. So here's my next rectangle. And between the 3 and the 4, the right side would be the 4. So here is my last rectangle. Now, after you've visualized this, you're going to compute or estimate this area by finding the area of each rectangle and adding them up. Now, Ms. Burko and I have a very specific notation that we use when we do this to keep our work organized so we don't make mistakes. And here's how we do it. We know we want 4 subintervals, so we're going to draw 4 lines. And we know we want to use the right side. So for each of those 4 lines, we're going to draw a vertical line on the right. This basically represents the rectangles, but we're only drawing in the right side to make it easier to remember which side we use to compute the height. Now the beginning of this subinterval is from 0 to 1 on the x-axis. The next one goes from 1 to 2. The next one goes from 2 to 3, and the next one goes from 3 to 4. So these are just numbers that represent where the rectangles start and stop on the x-axis. Then we're going to fill in the heights. The height at 1 is 4. Now I could get that by looking at the graph at this ordered pair, or I could get that by taking the 1 and plugging it in here. 1 squared is 1 plus 3 is 4. The height at 2 is 7. The height at 3 is 12. And the height at 4 is 19. So if each of these represents this imaginary rectangle that I'm finding the area of, now I know that since rectangles are just base times height, my base size here would be 1. From 0 to 1 has a width of 1. Here my base would have a width of 1. Here my base has a width of 1. And here my base has a width of 1. From 3 to 4, from 2 to 3, from 1 to 2. So I would just do base times height for the first rectangle, plus base times height for the second rectangle, plus base times height for the third rectangle, plus base times height for the fourth rectangle. And since I'm multiplying by 1, what I'm really doing is 4 plus 7 plus 12 plus 19. Now 4 plus 7 is 11. I'm going to add the 19 first because that's 30. Plus 12 is 42 is my total area. Now the reason we use this notation is having taught this for a while, we recognize that it's very easy to accidentally use the wrong numbers here when you're doing these estimates. And if you use the wrong numbers, you're going to get the wrong estimate. So we're going to require you to use this specific notation, which we're going to go through a few more times, to help you sort of make sure that you're organizing your work in a way that allows you to be successful. So let's take a look at number 2. Number 2 asks me to do the same thing. 4 subintervals between 1 and 4, or 0 and 4, but this time Elrom. So again, I'm going to divide up my graph into 4 sections. This time, to make 4 sections, I can divide it right nicely along the integers. Now instead of choosing the right side for each of my heights, I'm going to choose the left side. So my rectangles are going to look like this. Now you'll notice that's a very different picture than the previous problem. So again, we need you to know what these things look like. It is often a question on the AP test that which of the following represents a right side Riemann approximation, which of the following represents, and they'll show you pictures, a left side Riemann approximation. So you need to know what it looks like. So practice drawing these in. Now we want 4 subintervals. So just like last time, we're going to draw 4 little lines. And we're going to label the start and stop of each section. 0 to 1, 1 to 2, 2 to 3, and 3 to 4. However, unlike last time where I drew a vertical line on the right side of these, I'm going to draw a vertical line on the left because I'm trying to use a left side approximation. And then I'm going to get the heights of those rectangles. I could do that by looking at the graph. At 0, the height of the graph is 3. Or I could do that by taking 0 and plugging it into my function. When 0 is x, the y value is 3. At 1, the y value is 4. At 2, it's 7. And at 3, it's 12. So if I wanted to find these areas, I would do base times height. The size of this base is 1 times the height is 3, plus 1 times 4, plus 1 times 7, plus 1 times 12. So 3 plus 4 is 7, plus 7 is 14, plus 12 is 26. So we know that the actual area is somewhere in between 42 and 26. This one was a little too big, this one's a little bit too small. For number 3, use MRAM, but only use 2 subintervals. So if I'm going from 0 to 4 and I only need to break it up into 2 sections, then the middle would be at 2. So I would just draw one line in the middle. Now the height is going to be made by looking halfway in between those numbers. So halfway in between 0 and 2 is 1. So the height of this rectangle would be this guy. In between 2 and 4, the middle is 3. So the height of this rectangle is this guy right here. Now I only needed 2 subintervals this time. The beginning was 0, and then 2, and then 2, and then 4. Now the middle between 0 and 2 was 1, and the middle between 2 and 4 was 3. And we're using the middle to get the height. So I'm going to draw my vertical line in the middle this time. Now I can either look at the graph. When x is 1, the y value is 4. Or I could take a 1 and plug it back into my equation way up here and get 4. But the height would be 4 here, and the height would be 12 here. Now when I do base times height, the new thing here is that the width of my base got bigger. The width here is 2 spaces wide. So I would do 2 times 4 plus 2 times 12, which is 8 plus 24, which is 32. Last but not least, we're going to look at a trapezoidal approximation. So 4 subintervals, which means I'm going to divide it up right along the integers. And instead of using just the left or just the right, I'm going to connect them with a straight line to make a trapezoid. Now you'll notice this approximation method is the best one. It's actually pretty close to the actual area. And the more trapezoids we make, the better the estimate gets. Now when I show my work here, here's how we can organize ourselves. We have 4 subintervals, 0, 1, 1, 2, 2, 3, 3, 4. And we're going to write in both heights because the trapezoid connects the endpoints. Now it doesn't matter which of those lines you make taller than the other one. I just think drawing one of them taller than the other one makes it look more like a trapezoid. So the height at 0 is 3, height at 1 is 4, 4, 7, 7, 12, 12, 19. So when I do this approximation, I'm going to have to use my trapezoid formula. Instead of base times height, I'm going to do 1/2 height times base 1 plus base 2. So I'm going to have 1/2 times, now remember we said these are twisted, so the height here is actually this guy. 1/2 times 1, and then base 1 is 3, base 2 is 4, plus 1/2 times 1, base 1 is 4, base 2 is 7, plus 1/2 times 1, base 1 is 7 plus 12. Plus 1/2 times 1, base 12, and then 19. Now I'm going to use my calculator for this just because I don't want to make a mistake. And I got 34. All right, we're almost done. I know this is a bit of a long video. I appreciate you sticking with me here. The last thing we're going to look at is how do you use a table to get this information to estimate these integrals if you don't have a graph. So we're going to try to integrate from 0 to 9 using this table with the given number of subintervals and the specific type of method. The first problem says use RRAM with 4 subintervals. So I'm going to draw 1, 2, 3, 4 lines, and I'm going to put the heights on the right. Now if I look at the x values in the table, If I write 0, 3, 3, 6, 6, 8, and 8, 9 into my intervals, it divides nicely up into 4 sub-intervals. The height at 3, the y value would be 5. 6, the y value would be 4. 8, the y value would be 6. 9, the y value would be 8. So I would do, because these are rectangles, base times height, base times height, base times height. Now the size of this first base is 3. The size of the second base is 3, but don't assume all the bases are the same size, because the size of the third base is only 2. The size of the last base is only 1. So you can't just assume they're always all the same size. In the examples we just did on a graph, they were, but here they're not. So if I do base times height, I would have 3 times 5, plus 3 times 4, plus 2 times 6, plus 1 times 8. And I would have 15 plus 12 is 27, plus 12 again is 39, plus 8 is 47, is my approximation. Now I'm not going to make you do 6 and 7 right now in the video. We can definitely talk about those in class tomorrow, but I will say, why can't we use midpoint here? Well, in order to use midpoint, we need to know the y values at the middle x values. So for example, the middle between 0 and 3 would be 1.5. Well, because this is a table, we don't have a graph and we don't have an equation, we can't calculate those numbers. So because we need to know those and we don't know them, we can't use a midpoint approximation. So a lot of times with a table, they're going to ask you for left, right, or trapezoid, or they have to make the table in such a way that you can see the midpoint numbers. All right, thank you so much for watching and hanging in there. I know this was a longer video, but I think it was really important to make sure we are clear about this. This is a very, very difficult topic, and we can do really hard things if we put our mind to it. So we've got this. We'll practice it tomorrow.